It's a great pleasure to introduce good friend Dinshaw, who is giving the talk today. So Dinshaw is a master's from our own institute, IIT Kanpur, in physics. And after that, he went to UIUC to do PhD, and he was a postdoc in Johns Hopkins. And after that, he joined Notre Dame University as a professor. Dinshaw is well known for numerical schemes. I was in France, and they said, well, Dinshaw has a unique algorithms for pressure corrections, and so I'm not really in astrophysical simulations, but he's a very eminent scientist for numerical astrophysics. Okay, Dinshaw. So it's thanks to your visit to India that we are able to get a seminar from you. We wish that we were in person and we could really talk a lot about this stuff. But hopefully you'll visit us sometime in near future.
Sure.
Okay, Dinshaw. So please take over and start your talk.
Thank you very much, Mahendra. Very kind of you. And it's always a pleasure and a privilege to be here and giving a talk, especially at IIT Kanpur, which was my alma mater. Let's go ahead and get started. One of the things I would basically say is that please feel free to always, ask questions, because that's the only way we can make the talks lively, especially if they're virtual. So this talk is focused on introducing some numerical ideas associated with simulating problems in spherical geometry. And it's also oriented towards simulations that we have done recently, trying to understand magnetic O stars. And I would also like to point attention to a couple of people, Setu Subramaniam, who is a very good student of mine, very good prospect for hiring in a couple of years when he graduates, and also Sudeep, who is in the audience right now and has been very instrumental for this work, done very good work with me. So let's go ahead and launch into the talk. So for a long time, I've had this idea that, many of the problems in astrophysics require spherical geometry, and yet many of the problems that take place, many of the difficulties in simulating problems in spherical geometry are basically self-inflicted, in the sense that they're not genuine physical singularities, but they're just artificial coordinate singularities that occur when you have r theta phi geometry. And in that case, you have this obvious situation that the zones become smaller and smaller and smaller as you approach towards the pole of the spherical system. And as a result, it basically clobbers your time step. It also destroys your accuracy. And I've now found in the literature that there are codes out there in the astrophysics literature, namely the Pluto code and other codes also, which produce a lot of fictitious heating when gas goes over the pole of the simulation. And also magnetohydrodynamics has a divergence-free constraint, and that divergence-free constraint is very easily violated when one looks at the poles of the simulation. So it is highly desirable to actually go ahead and transition from the situation in the left in r theta phi geometry to the situation on the right, which actually shows you a geodesic mesh. And you can see out here that there are no coordinate singularities associated with this spherical mesh. And so if we can go ahead and do that, then we can overcome all of these four difficulties that we've discussed out here. And that would be very useful. It would be useful because it would actually allow us to do various physical problems in a much nicer way. Namely, it would allow us to solve for accretion disks, not just in shearing sheet geometries, but also for the full disk. It would allow us to study propagation of jets and galaxies. It would allow us to study star and planet formation. in India, there's a gigantic investment these days in studying the solar wind and its effect on the Earth's magnetosphere. This comes under the rubric of solar climate modeling, therefore understanding the heliosphere of our own star, of our own parent star, is very important. And what I'll be talking about today is understanding magnetospheres of other stars and planets. And there are all sorts of other issues, like, namely convection and dynamos in the sun, convection in AGB stars, possible applications to protoplanets. Again, India is big on global weather modeling these days. And because we're modeling turbulence and MHD turbulence, we would actually like to arrive at higher order schemes that are impressed on these spherical systems. So we would like to actually solve a lot of these problems. And therefore, the structure of the talk is that in the first and second units, I'll talk about geodesic meshes and their advantages and how the sphere is meshed up. And I'll also talk about high accuracy algorithmic issues. And this is just very brief, very cursory view of things. And then we'll basically launch into the physics of radiation-driven winds in massive stars. We'll talk about the three important parameters that regulate the simulations of magnetized winds around massive stars. And then we'll talk about mass loss approach to quasi-steady state. We'll intercompare dynamical magnetospheres with centrifugal magnetospheres. We'll talk about mass and angular momentum loss, and then we'll talk about conclusions. So how do you mesh up the sphere? The answer is that you basically try to arrive at the most uniform meshing of the sphere, and that will hopefully allow us to eliminate the coordinate singularities, thereby allowing us to get larger time steps, better accuracy at the poles. We completely bypass all issues of fictitious heating at the poles and the divergence-free or the loss of divergence free aspect in the magnetohydrodynamic simulations. That all comes about by essentially going to Platonic solids. So, more than 2,400 years ago, Euclid understood that these 5 or 6 perfect geometrical figures, and this is one of them. It is an icosahedron, which consists of 20 equilateral triangles put together. And if you go ahead and just blow up such a triangle, you basically blow up such an icosahedron, you basically get to a shape like this, where you have essentially 20 great triangles on the surface of a sphere. And these 20 great triangles on the surface of the sphere make an angle of 63 degrees, 63.9 degrees relative to the center of the sphere. And that's kind of gives you a very coarse mesh approximation of the sphere. But you can actually go ahead and do recursive subdivision of that same geometry, and you arrive at geometry like this. And if you continue this recursive subdivision of each of the parent triangles for several more iterations, then you can actually go ahead and arrive at a spherical mesh like this, which is a very beautiful mesh because it gives you an angular resolution of around 4 degrees relative to the center. And that's kind of a mesh that we would like to simulate in. In actuality, the meshes that I will be simulating on have about a 2-degree resolution. And this actually allows you to take each of these differently colored triangular patches and send them to different processors. So in India, there's a huge emphasis these days on parallel processing. The government of India seems to give enough money to buy like 1,000 or 2,000 core supercomputer to each of the institutes. And in that case, you can actually go ahead and do parallel simulations very efficiently on these meshes. So there are great opportunities out here. And we realized that in the previous transparency, I just showed you the 2-dimensional covering of the sphere, but we would actually like to go ahead and do 3-dimensional simulations. And what is done is that each of these two-dimensional triangles is actually extruded in the radial direction, so that you have a mesh like this with zones that can look essentially like this. And because the zones are like this, they appear, or they have the structure of a triangular prism. So we have a situation where the zones actually look like this shape out here, which is called a frustum. But this frustum is logically equivalent to a triangular prism like the one shown out here. And therefore, we can actually go ahead and say that in order to do these simulations, you have to be able to discretize volumes, areas, line elements on the geometry. And by using a methodology called isoparametric mapping, we can actually go ahead and take the information known that on this structure and basically translate that to the information on this structure. And you can actually see that here, for example, at this nodal point, the volume is smaller because you have this radial constriction. And at the analogous nodal point out here, the volume is larger. So this shows you that the geometry structure is built in. There's a chat out here. So let me go ahead and see what the question is. Okay.
No, I just asking everybody to
That's
mute.
okay. I understood. So we can actually go ahead and do that. And what we need to do is essentially solve Faraday's law in the MHD equations. And the gold standard for doing that is to actually do the constraint transport update, which basically collocates magnetic field components at the faces of your zone and has electric field components at the edges of your zone, and then actually goes ahead and does a divergence-free update of Faraday's law. So we can actually play the same trick on this frustum shape that we get in spherical geometry. So we actually collocate magnetic field components at the faces of the mesh, and then we collocate electric fields at the edges of this zone, and then we can actually go ahead and do everything. There's some nice technology that we've invented along the way, like multidimensional Riemann solvers, etc., which will actually allow us to do that. And this is a very nice scaling diagram.
Let me ask you a stupid question. So I don't know this method well. So you are solving in some kind of cubical box and you are transforming it to sphere. I mean, this mesh, what does it? So
this actually looks like one zone of this mesh out here.
Okay.
Okay. So if you look at this zone, it looks logically like a triangular prism. And therefore, I've basically shown how to solve the MHD equations, namely Faraday's law, along with, of course, the hydrodynamic equations on such a structure.
Okay.
So this is kind of a nice scaling diagram. I mean, you know, if Sudeep made this nice diagram, which shows that even for 100,000 cores, we can actually achieve very good scalability. So we can actually go ahead and reach petascale and exascale computations, which are actually now very popular in the United States. And India is also getting into them. So the bottom line is that let's now turn our focus to the physics of winds around massive stars. And
one more question. Just one more question.
Yeah,
so
go ahead.
It's an incompressible or compressible flow?
This is compressible. Everything is compressible.
Okay. And but del dot B
are really supersonic.
So communication is with nearest neighbors. Is that correct?
Yeah,
processor.
That's right. Yeah, that's right.
Okay.
Okay.
Yeah, so, please go on. Yeah.
So basically, what distinguishes a very massive star? The answer is that if you have a 30 or 40 solar mass star, it will have a luminosity that is about 1,000 to 10,000 times the luminosity of our sun. And as a result, the radiation pressure is so strong at the surface of such a star that it can basically blow off a gigantic wind from the surface of the star. So typical massive stars will have wind outflow rates of 10 raised to minus 6 m solar per year, which is dramatically larger than the wind outflow rate that is taking place on the surface of our sun, which is more like 10 raised to minus 14 solar masses per year. And of course, the processes that drive the solar wind at the base of the solar corona are very different from the processes that drive the winds around massive stars. The processes that drive winds around massive stars is basically the radiation pressure, whereas for the sun, the radiation pressure is minuscule, and what drives the wind is essentially magnetohydrodynamic processes and turbulence and all that, all of the good stuff that Professor Varma works on. So with that, we realize that there's a qualitative difference in the sense that the sun, over the whole course of its lifetime, will only lose about 0.01% of its mass, whereas a massive star can lose more than 50% of its initial mass. And this has important consequence because you could have a 25 solar mass star, which is a very massive star, which is an OB star, and over the course of its lifetime, it will lose about half its mass. So it will actually become a 12 and a half solar mass star by the time it gets to the supernova death point. And so it actually tells you that stars that are starting with a certain mass will wind up with a very different mass when they go supernova. So it helps to actually understand the comprehensive evolutionary history of massive stars, which is in fact regulated by the winds that they drive out. And these winds that they drive out are actually doing a lot to change the interstellar medium. For example, you can have chemical evolution of our galaxy. You can have mechanical energy being input through these winds. These winds can actually ionize parts of the interstellar medium and drive subsequent generations of star formation. So the basic idea behind this massive star winds is actually Doppler shifted resonant absorption of UV radiation. And so let's go ahead and talk about that for a few minutes. And here's an example of that. So let's go ahead and say that the radiation, the amount of luminosity in a massive star is about 1,000 to 10,000 times the luminosity of our sun. And furthermore, the luminosity all comes out in the ultraviolet because the surfaces of these stars are around 20,000 to 40,000 degrees Kelvin. And as a result, what I want you to do is imagine the trajectory of a photon, a radiation line coming that is emitted by the parent star with a wavelength of lambda 0. Okay, now this radiation cannot be immediately absorbed by the wind that is taking place around the star. So we are actually showing you out here the velocity of the wind as a function of radius out here. And what is actually happening is that as the photon that is emitted from the surface of the star makes its way outwards, it actually runs into wind that is Doppler shifted away from it, and therefore it cannot undergo resonance scattering with the material in of the wind that is in front of it, till it reaches a certain radius where again that line is brought back into resonance, maybe with another resonant line, and maybe at this radius you have an interaction between the wind and some other resonant line, so that over a short range of radii, you can actually have this photon resonate with the lines at that radius. And then you will have scattered photons kind of going inwards or outwards and so on and so forth. And of course, the energy of the photon is degenerated at that point and the photon moves on. So this is the physics behind line scattered radiatively driven winds. And by the time we kind of put it in our simulation code, we basically make even further simplifying approximations so that we actually go ahead and just focus on the acceleration of the wind material, which is actually this guy, acceleration as measured along the radius, so it's dv by dr. And this actually allows us to arrive at a radiative driving acceleration, which is this guy, and we put that into the code and we are off to the races. So there's a further instability that can actually cause clumping in the wind, but I'm not going to mention that because that's not the physics that we're interested in tracking down in these simulations. But we are interested in tracking down this, the physics associated with magnetic activity in these massive stars. So it actually turns out that 7 to 10% of these massive stars have extremely strong magnetic fields. And the interesting correlation out there is that if you go ahead and look at neutron stars, which are the end state of these massive star evolutions, then about 10% of these neutron stars will have extremely powerful magnetic fields, which causes them to be classified as magnetars. So there's probably an evolutionary connection between massive stars with strong magnetic fields and the end state resulting in magnetars. So how does this magnetic field arise? It actually turns out that the outer layers of a massive star are radiatively stable and they do not undergo convective processes. So it's impossible to drive a dynamo out there, but there's some theories which say that maybe some near the surface convection zones can actually go ahead and drive a dynamo out there. It actually turns out that the centers of these massive stars are in fact strongly turbulent, so you can actually drive a dynamo out there. And it may also be that these stars acquire these magnetic fields basically as part of the interstellar magnetic field that is dredged in when these massive stars form. So we actually just work with the empirical fact that about 7 to 10% of the stars have been observed polarimetrically to have very strong magnetic fields. And then we kind of go ahead and ask what are the consequences of having a very strong magnetic field. So let's go ahead and now delve a little more deeply into the consequences of having a magnetic field. And so this blue structure out here is actually the star. You can imagine that the z-axis is the axis along which the rotation is taking place. So I'll always use my finger to show the z-axis along which the rotation is taking place. I hope you can kind of see that. And the magnetic dipole axis can make essentially any angle relative to that z-axis. And so the magnetic dipole in this picture is shown out here, like so. So you actually have a situation where if this magnetic field is weak, then the ram pressure of the wind will basically blow off that magnetic field and basically shred it and result in just open field lines. But if the magnetic field is strong, as it is for these magnetized stars, then you have a different phenomenon happening where you can actually see that the magnetic field lines will take the wind that comes out from here and basically bend it along this way, and likewise the wind that comes out from here and bend it along this way. So the question is exactly what is the parameter that regulates this process of the bending of the wind, and we can actually go ahead and quantify that by taking the ratio of the magnetic pressure to the ram pressure, and we come up with a magnetic confinement parameter, and that tells us that if this magnetic confinement parameter is much larger than unity, then the magnetic field can actually play a dynamical role in confining the wind that is coming out. And now realize that the magnetic field for a dipole actually falls off as 1 over r cubed, which basically means that this magnetic field is only going to be strong out to a certain radius. And that radius out to which it is very strong is called the Alfvén radius. And so we realize that as the magnetic confinement parameter increases, the Alfvén radius will increase. And the physics of the Alfvén radius is such that basically the wind will co-rotate with it will co-rotate in a rigid body fashion with this magnetic field, which is in fact anchored on the star. So it will actually co-rotate in a rigid body fashion with the rotation speed of the star itself, as long as it is within this Alfvén radius. Once the wind gets out of the Alfvén radius, of course, it is not held by the clutches of the magnetic field, and it's free to kind of go ahead and flow away. So that is one piece of physics that was governing this problem. What is the other piece of physics? The answer is that many of these stars can actually undergo common envelope evolution, which basically causes the star to spin up quite dramatically. And we can then ask, what is the extent? What is the maximum extent to which you can spin up a star? And the answer is that you just equate the centripetal acceleration to the gravitational acceleration, and you come up with this critical rotational angular velocity with which you can actually spin up the star. So we come up with the idea that there is a critical rotation ratio, namely no star can spin up faster than this critical ratio, but you can actually take the ratio of its true angular velocity relative to the critical angular velocity. And then you can actually ask, what is the radius beyond which in a rotating frame the centrifugal forces will win over gravity? And so you can actually go ahead and compare the centrifugal forces to the gravitational force, and you can actually come up with this relationship, which is called the Capillarian radius. So it basically says that in a rotating frame, when you go past the Capillarian radius, your centrifugal forces will take over and play a much more dominant role compared to the gravitational forces. Now, of course, in order for those forces to take a hold, you have to have a situation where the magnetic field keeps the outflowing gas in lockstep with it and makes it rotate at that angular velocity. So we arrive at another characteristic radius, and we realize that as this critical rotation ratio increases, the Capillarian radius moves inward towards the star, and that's another important scaling that we should remember. And the third parameter that regulates this process is actually the angle between the rotation axis and the magnetic dipole axis. So we'll actually have two equators, namely we'll have the rotational equator and we'll have the magnetic dipole equator. So you can actually now go ahead and apply this to one of the leitmotif stars, namely one of the characteristic stars, namely Zeta Pup. But of course, the theory is completely general, which we've developed, and we can apply it to any star. So you actually have a situation where you have a magnetic wind confinement parameter, and associated with that, you can arrive at an Alfvén radius. Please keep in mind that as long as the material is within the Alfvén radius, the magnetosphere of the star, namely the magnetic fields of the star, keep the wind material in rigid body rotation, namely the torques from the magnetic field basically spin the material that is coming out to the point where the wind is actually in rigid body rotation with the star. And as Eta star goes up, our Alfvénic radius, or A, increases. Okay, then there's the rotation ratio, and the physics of that rotation ratio is that as the Capillarian radius, if you can keep the material spinning, then indeed the centrifugal forces will actually fling the material outwards. So we have the physics that as W increases, our Capillarian radius, RK, actually decreases. And then, of course, the third parameter is this angle of the tilt between the rotation axis. So I'll always use my finger to show the rotation axis, and I'll always use my pen to show the tilt of the dipole relative to the rotation axis. So we actually come up with two possible end results. We can actually have a situation where we have a slow rotator, namely, in this case, omega is small. And if omega is small, then RK is large, and therefore the Alfvén radius is smaller than the Capillarian rotation radius. And therefore, we have a situation like this out here, where we have a dynamical magnetosphere. Namely, in this region out here, up to this Capillarian radius, the magnetic field keeps the material in lockstep. The Capillarian rotation radius is larger than the Alfvén radius, which basically means that once you get past this point, the centrifugal forces cannot work on the material simply because the material is now in free expansion away from the center of the star. But notice the other case, which is the fast rotator case. If omega is large, then the Capillarian radius becomes small, and you can actually have a situation where the Alfvén radius is larger than the Capillarian radius, and you have this lower panel out here, where you can actually have a situation where the magnetic field holds the outflowing gas in lockstep all the way out to the Alfvénic radius. But what happens past the Capillarian radius, namely what happens past this radius, is that the material is actually co-rotating with the star, and therefore, so the centrifugal forces can basically start to spin up the material and fling the material outwards, and therefore you have this resonance taking place between the Capillarian radius. So the important question that we have out here is that all of the stuff that I've described is just theoretical stuff associated with a aligned rotator, namely the axis of rotation and the axis of the magnetic dipole are lined up. But how does all of this change when we go to the non-aligned case? So let's go ahead and understand how this happens. So we've done a whole range of simulations. And out here, I can actually show the Capillarian radius of the simulation and the Alfvén radius. And the first two simulations are non-rotating versus rotating. So this one is non-rotating, and I'm having a rotating situation, but with no magnetic field out here. You can see that with the 0 eta star. Then we can actually go ahead and have a situation where this situation out here has a strong magnetic field, but no rotation. And then we can go ahead and spin up the magnetic field or spin up the star. And we can also go ahead and have different spin angles of tilt between the magnetic axis and the rotational axis. And this set of simulations shows a situation where we have an even stronger magnetic field, again with the same aligned and non-aligned cases. And in each case, we can actually compare the Alfvén radius to the Capillarian radius. And if the Alfvén radius is less than the Capillarian radius, it's a dynamical magnetosphere. If the Alfvén radius is more than the Capillarian radius, then we have a centrifugally driven magnetosphere, exactly as shown in these two different schematics out here. So this is dynamical magnetosphere, and this is centrifugal magnetosphere. Okay, so once we have that, let's go ahead and see what happens. So we go ahead and start a whole bunch of simulations, on our big supercomputers, and we can actually go ahead and trace out what happens in the simulation. So we start the simulation with a certain characteristic outflow rate, and then we watch what happens as the simulation achieves a quasi-steady state. And you can actually go ahead and see that if I have a smaller magnetic field, which is shown by the blue line, then I have a larger mass outflow compared to the situation where I have a larger magnetic field shown by the red line, where I have a smaller mass outflow. And this makes sense because the magnetic field is good at trapping the outflow and therefore preventing much outflow from happening. And you can see the same trend when you have rotation thrown in, but no tilt, and rotation thrown in with a certain amount of tilt, and rotation thrown in with a larger amount of tilt. So the trend line in these simulations is that as you crank up the magnetic field, you will have lower mass outflow in the star. So that's our first observation out here. And let's go ahead and firm up this observation and understand many further aspects of it. So the left panel out here shows the density of the wind as a function of radius. The middle panel out here shows the radial velocity as a function of radius, and the right panel out here shows mass outflow rate as a function of radius. So let's go ahead and compare the fiducial situation with no rotation and no magnetic field, which is shown by the black curve out here, to the situation where we have, in fact, some rotation but no magnetic field. And so we see that when we spin up the star, you actually have a higher mass outflow rate. So increasing rotation will actually increase the mass flux from the star. Now let's go ahead and compare the other scenarios. So if we have our fiducial case with no rotation and no magnetic field, and we actually go ahead and throw in a magnetic field out here, then we go from here, the black line, to the orange line out here. And so we see that introducing a certain amount of magnetic field actually causes a decrease in the wind outflow from the star. And that's an interesting observation, and it will have some pretty interesting physical consequences later on. Now let's go ahead and compare our fiducial magnetized case with a case where we have magnetism as well as spin. So then we go from this orange curve out here to the purple curve out here. And that allows us to realize that introducing a magnetic field, increasing magnetic field, and introducing rotation with that will also increase the mass flux. So increasing rotation, even in the magnetized case, increases the mass flux. And interestingly, increasing the magnetic field will actually decrease the mass flux, which we saw in the previous point that I made. Now let's see what happens if we take our fiducial case, fiducial magnetized case, which is again this orange curve, and compare it to these two guys out here. So if I introduce more and more tilt, I see that I have a reduction in the amount of mass outflow. And this is actually interesting and makes sense, because as you increase the tilt between the rotation axis and the magnetic dipole, the moment arm that you get is actually reduced. Namely, you have a cosine zeta variation of the moment arm with which the material can be flung outwards. And therefore, because of that, you actually have a reduction in the outflow. So with these trend lines established, now let's go ahead and have some fun, because we can actually, because these simulations actually lend themselves to very vivid movies. So this is your typical magnetized case with no rotation and no tilt. And in that case, what you see is that the alphane radius is 2.1 times the radius of the star, and the Capillarian radius is infinity. And because Ra is less than Rk, we have a dynamical magnetosphere. So let's go ahead and roll this simulation. And what we expect is that the magnetic field is strong enough to basically constrain the matter and prevent it from flowing outwards. And here you saw exactly what it did, namely it formed a clump. And now we are seeing the second clump from forming, and the clumps basically cannot escape the clutches of the magnetic field and therefore rain down on the star. And in doing so, they basically go ahead and fill in the magnetosphere of the star. So as time progresses, you are actually seeing these regions out here getting filled up with matter that has rained back down on the star because it couldn't escape the clutches of the magnetic field. So with this, we get our first insight that we get filled magnetospheres, classical looking magnetospheres, if we have a dynamical magnetosphere situation. Okay, so that's your third clump going and falling onto the surface of the star. And there's no point running the simulation for much longer, because you basically have a quasi-static situation, and it will keep doing this forever if we let it run for longer. So let's go ahead and now look at another situation where we again have the same magnetic field, but we've now spun up the star. So if we go ahead and spin up the star, then we have a situation where the alphane radius is 2.1 times the radius of the star, but the Capillarian radius is 1.59 times the radius of the star. So we expect this to be a centrifugal magnetosphere, but let's see what we actually get. And we see that what happens is that the magnetosphere starts filling up, and you're actually now going to see the first clump from forming in a few seconds. Yes, that's the first clump falling down, and you'll see a second clump falling down also. And you'll actually now see multiple clumps falling down onto the surface of the star and filling up the magnetosphere exactly as it did before. So you have a situation where you pretty much thought you were going to get a centrifugal magnetosphere, but because the Capillarian radius is so close to the alphane radius, you actually get a dynamical magnetosphere. Go ahead. Okay. So now let's go ahead and crank this up even further. So we now have an extremely strong magnetic field and some rotation. And now we can go ahead and ask what happens. So here, the alphane radius is clearly much larger than the Capillarian radius. And we expect to see a centrifugally driven magnetosphere out here. And so let's go ahead and see what happens. And we indeed see that that's exactly what happens. Namely, we have very little clump formation or no clump formation, but you have these outer magnetic field lines that are basically oscillating back and forth because you have a centrifugal magnetosphere being set up. In other words, the Capillarian radius is much smaller than the alphane radius in this situation. Okay. And you can see the outermost field lines fluctuating in time out here. And so with this, let's go ahead and proceed further and now study the effect of tilt. So now we have a situation where the rotation axis is this way in the direction of my finger, but the magnetic field, magnetic dipole is actually oriented this way. Now we would expect that because RA is comparable to RK, we should expect, or larger than RK, we should expect a centrifugal magnetosphere. But we actually realize that because the moment arm available to the system is just RA times cosine zeta, that number is actually comparable to RK. And so we actually expect it to be a dynamical magnetosphere. And let's go ahead and run the simulation. And you can see that this is a dynamical magnetosphere. I'd also urge you to see that now the clumps do not exactly rain down on the star. And you can actually go ahead and see that the outflow takes place from the foot point that is closer to the equator, which is no surprise because that's where you have the larger amount of centrifugal forces. So now let's go ahead and see what happens if we really crank up the magnetic field. Notice that this should have been classified as a centrifugal magnetosphere, but because of this cosine zeta factor, we expect it to become a dynamical magnetosphere. And let's see if that expectation is borne out. And we see again that the clump formation is again taking place and the clumps begin to try and rain down upon the magnetosphere. But there's a very interesting phenomenon that takes place, which is to say that the magnetosphere is not the classical magnetosphere that is filled in from both sides, but rather is filled in a non-axisymmetric fashion, as you see happening out here. So this is the physics of the dynamical magnetosphere taking place. And it takes place for quite a while. And then now let's go ahead and see a situation where we have the maximum amount of tilt. And now again, you expect in principle to see a centrifugal magnetosphere, but it turns out to be a dynamical magnetosphere because of the inclusion of tilt. And you can see the clumps forming and falling down upon the star and actually going and filling up the magnetosphere of the star, as you see out here. So with that, you can actually see the magnetosphere being filled up out here and out here by the clumps that are falling down on the star. So with that, I can actually show you the three-dimensional structure of this wind, but it's not of great interest. So let's go ahead and skip that and get to a more physicsy part of things. So now realize that the system has not just matter flowing and being flung outwards, but it also has magnetic field lines. And the interesting thing about magnetic field lines is that just like matter can actually have an angular momentum flux, the magnetic field lines can also, because by virtue of the magnetic tension that they can generate, they can also produce an angular momentum flux. And this out here shows you an aligned rotator at the top left panel. And what I'm showing you out here is the full simulation and a kind of zoom in of the central region of the simulation. And if we ask where is the angular momentum largest, when we focus close to the star, it's actually the largest out here. And it's actually largest along the open field lines where the magnetic torques are the largest in going ahead and spinning up the material that is coming outwards. If you go ahead and look at what is happening at a larger distance, for example, out here, you realize that now the matter has begun to dominate relative to the magnetic field. And so we have a situation where we understand why the magnetic torques are basically spinning up the material that flows outwards. Of course, angular momentum is conserved. So if the magnetic fields that are anchored in the star will spin up the material that is flowing outwards, then there's also a consequence that the star itself, because it anchors those magnetic fields, is going to lose angular momentum. And that's actually what happens, namely the star loses angular momentum at the same rate as the angular momentum in the wind is spun up and flows away from the star. Now, this is actually showing you a tilted situation, this middle panel, and you can actually see that the angular momentum is largest along these open field lines all over again. And this lower panel is showing you the maximally tilted situation, where again, you're seeing the largest sources of angular momentum out there along the open field lines, especially close to the star. So this can actually be plotted up, and I've plotted it up on the surface of the star. And you can actually see that because of the episodic clump formation, which is shown out here, you can actually have episodic intense mass structures coming out from the material. And you can also have angular momentum being flung outwards in episodic moments in this situation out here. So that's showing you the thing visually. What I've also done out here is plotted it out as a function of radius. So actually, this shows you the angular momentum flux as a function of radius in each of these simulations. And this thick black line shows you the total angular momentum, whereas the thick red line shows you the time averaged angular momentum flowing out because of magnetic tensional forces. And the blue line out here shows you the angular momentum flowing outwards because of the matter or along the gas-based sources. And you can actually see that the total angular momentum is constant, but there's a switch, namely close to the star, much of the angular momentum that is flowing outwards because of magnetic tension. But as you go farther out, much of the angular momentum that is flowing outwards is due to the mass of the material matter in the wind that is flowing outwards. And you can see this out here in all these three panels. And you can also see that as the star is made more and more magnetized, then the magnetic field carries more angular momentum outwards from the star than the matter does at any given radius. Now, these thin lines that you're seeing out here are plots of the angular momenta from the three different sources, namely the total, the magnetized, and the material. And you're seeing that you have a substantial amount of variation as a function of time, which actually makes sense because you actually see the clumps forming and coming out and carrying angular momentum off with them. So with this, we can actually, okay, so this was all visual, just to kind of give you a sense of it. But now we can actually extract two very important timescales from this problem. The first time scale that we can extract is the rate at which the star loses mass, and that's this guy out here and this column out here, and we've extracted that for each of the simulations. And the second important parameter that we can extract is the rate at which the star is spun down. So let's go ahead and first focus on the first column associated with the mass timescales. And we see that if we have a non-magnetized situation, which is the one out here, you can have a time scale for the mass loss, which is rather small. Namely, these massive stars typically live for around 10 million years. And you can see that the time over which the star loses a significant amount of its mass is actually 16 million years, which basically means that the star loses a significant fraction of its initial mass over the course of its lifetime. And that's very significant. Now, let's, however, compare it to these four guys out here. These 1, 2, 3, 4. Okay. And that actually shows us a very different story. So if I compare it to these four guys out here, I actually see a very interesting story, which is to say that the time scale over which mass is lost is actually much, much larger now. What does that mean? It basically means that over the course of the lifetime of the star, which is around 10 million years, the star loses a much smaller fraction of its mass. And so the presence of magnetic fields is actually very good news for mass loss, because we would like the star to arrive at its final state with most of its mass intact, so that you could actually get a good bang from the supernovae. And in fact, we see that strongly magnetized stars actually manage to retain much of their mass. And that's shown even more compellingly in these four lines, where you can actually see that the time scale for mass loss has increased even more because the magnetic field has increased even more in these simulations. So this tells us one important piece of data, namely that the magnetic fields in these massive stars are very effective at holding on to the mass, and therefore making sure that you get bigger bangs from the supernovae that will eventually happen as these stars die out. Now let's go ahead and ask another important question, which is to say that what is the angular momentum loss rate? And you can see that out here, which is to say that the angular momentum, the time scale over which the star loses a significant amount of its angular momentum, is in fact very, very small. Okay, and this actually makes sense, and it matches up with observations, because many of these highly magnetized stars are known to be slow rotators. And we see now that the spin down rate for the stars is very, very fast compared to their lifetime. So in other words, even if the magnetized star begins as a very fast spinning star, it will actually lose much of its angular momentum very, very fast and become a slow rotator very quickly. And that actually is consistent with the physics of the problem, or that is actually consistent not just with the physics of the problem, but it's also consistent with observations of stellar rotation. So this is actually making sense, and it makes good sense now. So we can come to our conclusions, which is to say that we've shown that very interesting simulations can now be done. We've opened up a new chapter in being able to simulate spherical systems, and we can simulate mass. When we've applied that numerical capability to understanding massive magnetized star winds, and we simulate the simulations to quasi-static steady state, and we can actually now, because of the complete geometry independence of our simulational capability, we can actually study tilted dipoles in a very dramatic fashion. And we have episodic mass loss events. We also realize that the effect of rotation and magnetic fields on the outflow rates. And we've been able to extract the mass outflow rate and the spin down rate for these massive stars, and we get some very useful insights onto the role of supernova progenitors. And then we can actually extract signatures for H-alpha, X-ray, and radio emission in these stars. So with that, I will actually thank you for your attention. And if I might indulge myself just a little, I'll actually point out that there are many more talks coming, and I will email this document from this transparency to Professor Verma. For those of you all who are younger people, it might make sense to actually go ahead and understand the numerical algorithms that go into capabilities like these. I'm actually here as a Varja faculty, thanks to the Indian government, and I'll be giving an entire sequence of talks out here at these particular dates, and younger people who are interested in computational methods and their applications can actually go ahead and please attend these talks, and I would be very grateful to see you all there. So with that, let me go back and ask, open the floor up for questions. Thank you.
Thanks, Dinshaw, for very exciting talk.